All right, so we're going to do a quick review of section 5.1. This is dealing with solving systems of linear equations by graphing. Now, a system of linear equations, so a key word, we know what linear equations are, but this is talking about a system of linear equations, which basically is two or more linear equations having the same variable. So it's when you have two or more linear equations and they all have the same variables. Now, the solution to a system is an ordered pair that satisfies all equations simultaneously. So it could be one ordered pair, it could be several ordered pairs, but it has to satisfy all the equations of the system to be considered a solution. Some have no solutions, and some have many solutions, and some have just one ordered pair solution. So let's look at this particular example here. It says, determine if the given points is a solution to the system. So they give you 3 points. And here's two linear equations. Remember, the definition of a system is having two or more equations. So we need to determine which one of these points will satisfy both equations. All right? So the first thing we're going to do, let's do the first one. We're going to just plug in these points here, 3 and 2, for the x and the y. So we have 2 times 3 plus 3 times 2 equals 12, which is 6 plus 6 equals 12. 12 equals 12. So this is a true statement. Let's try it on this one. We have 3 times 3 minus 2, 7. So we get 9 minus 2 equals 7. 7 equals 7. So this is true. So since this point here works for both equations, then you can say that 3.2 is a solution. Now let's look at the two equations again, and let's try our second point. So I'm going to move this up. Here is our equation that we started with. And I'm going to plug in 2 and 1. So 2 times 2, 3 times 1. Just go ahead and do it over here. 2 minus 1. So this is going to give me 6 minus 1 equals 7. 5 equals 7. So this is false, right? So that's false. This one's going to give me 4 plus 3 equals 12. So this gives me 7 equals 12. And so that's false. So in this case here, you would say that this point, 2.1, which is what we were testing, is not a solution. In fact, once you could have just done this one here and not even worked at this problem, because once you get one of them to be false, you can stop right there and say this isn't a solution. Because remember, it has to be a solution. It has to be a solution for both. All right? Let me give you an example of that. Let's take this particular point and let's try it if we can. All right? So let's take our original equation. 2x plus 3y equals 12. 3x minus y equals 7. I'm going to plug in my point. Remember, my point is 3/2, 3. That's the one that I'm testing. So 2 times 3/2 plus 3 times 3 equals 12. I'm going to plug it in over here. And let's go ahead and simplify. These cancel out. It's the same thing as like 2 over 1. So it cancels out and gives me 3. 3 plus 3 gives me 9. And 9 plus 3 gives me 12 equals 12. So this is true, right? So that's true. Let's try this one. This is 3 over 1, which is going to give me 9/2 minus 3, correct? Equals 7. And basically you're going to make this 9 halves minus 6 halves, because remember 6 halves is the same thing as 3. Got to have common denominators before, and 9 minus 6 is 3. So you end up with 3 halves equals 7. Well, that's false. So remember, this has to work for both equations, or if you had 3 equations, they have to work for all the equations to be a solution. So since one of them is false, you would say that this point here is not a solution. All right? All right, so now one way to find a solution to a system is by graphing each equation on the same pair of axes to see what common point or points they have. All right, in other words, if you graph them, if they have common points, then you know it'll work for both equations. So that is the one way. So let's go ahead and discuss some different possible solutions. All right, so on page 155, there is a table, but let's go ahead and talk about it. There are 3 possibilities, all right? The first possibility, if I had 2 equations, and let's say I graphed line 1 and it looked like this. Oops, I graphed line 1, it looked like this. And then I graphed line 2, all right? It looked like this. This point where they intersect would be the solution, all right? And it would have just one solution because there's only one point that would satisfy this line and this line. So, and this intersecting lines have one solution. The other thing you can say is they're a consistent system. And you can say it's independent as well. Now basically, a system of intersecting lines, or if they're the same line, all right, we call those consistent systems because at least one, they have at least one solution, okay? So let's look at another example. So this is intersecting lines. Another way you could have graphed your lines, what if this was, if you went ahead and graphed a line here, and then you ended up graphing the second equation here, and it ended up looking like this on your x and y axis, you end up with parallel lines, right? Well, parallel lines have no solution, right? Because there isn't a point that they have in common, so there's no solution. And we're going to call this inconsistent system. And we're also going to call it independent as well. And the third type you could have is what we call coincident lines, okay? And so that would be like if I graphed the first line, all right? And then I graphed the second line, and it ends up that line 2 and line 1 are basically on the same line. They lie on each other, right? So they are going to have infinite solutions because that means every point on the line is a solution. So they have infinite solutions, right? And we call this one a consistent. Now remember, consistent is meaning that it has at least one solution. Remember, this was consistent, it had one solution. This is called inconsistent because it has no solution, okay? So if they lie on this, they're both the same line. It is a infinite solution. It's consistent, and it's also called dependent. It is the only one here that is a dependent equation, whereas these are independent equations. Dependent equations form a consistent, but independent equations are unrelated equations that form either a consistent system. So these are unrelated. There's no relationship between them here. they have no solution, so it's independent. Okay? And so they're called that independent. So there's no relation. This one has no relation except for the 1. This one is dependent because they are related. So when graphing linear equations, you can use any method that you learned in Chapter 3. You just decide which method is the easiest or the best, depending on what you're given. Okay, so when graphing linear equations, you could do that. The first thing, so what are the 3 different ways that we have learned about graphing in Chapter 3? Well, we learned you can prepare a table of values. In other words, just pick a letter for x, find out what y is, right? You remember that? When you did this, x, y, x and y, and you said, okay, if x is 0, what is y? When x is 1, what is y? Okay, remember doing that? That's one way. The other is you can solve for the x and y axis, intercepts. Remember, that's when if you let x equal 0, what is y? And what is x when that is y? So that's one way you could do it. And of course, remember the third way is when you get this slope-intercept form. You can use it. Here we have the slope-intercept form, y equals mx plus b. So basically, you would find the y-intercept, which is 0b, plot it. Then you're going to use your slope m to find the point. Remember, slope m is rise over run. Okay, so these are the 3 different ways that you learned in Chapter 3. And you can use any one that you want when graphing linear equations. Just determine which one is the best use, unless they specifically ask you to use a certain one. All right. And then if you look on the page 156 at the top, there's a chart. It says the solving system graphing. There's steps. So you can look at that and go through the steps. I'm going to go ahead and we're going to do one. So this one says, solve the system by graphing. So it's telling you how they want you to solve the system. It's by graphing. So here's one equation and a second equation. So these are our 2 equations in the system. So I'm going to use the y-x-intercept by plugging in my zeros for x and y. Okay, so let's do that. I'm going to take this equation here. I'm going to plug in 0 for x and solve for y. And I get y equals 9. On this one here, I'm going to plug in 0 for y, right? Just find out what x equals. So in this case, when x is 0, y is 9. In this case, x is 9 when y is 0. So these are my y-intercepts and my x-intercepts for this equation. Let me find them for this equation over here. Again, you're going to do the same thing. I'm going to plug in 0 for x and solve for y. In this case, I'm going to get y equals a -5. Plug in 0 for y, and I get x equals 5. So my point here is 0, -5, and my point here is 5, 0. So there's my 2 points for this equation. Here's my 2 points for this equation. I'm going to graph I'm now going to use these points to graph my line. Okay? Let's see if that helps a little bit. So notice we have 9, 9, and 5, and 5. And so they're odd numbers. So I just chose to make my number systems the odd numbers, 1, 3, 5, 7, 9, 11. You could do 1, 2, 3, 4, 5, or you can count by twos. You just kind of pick how you want to mark your units. So in this case, this one is 0, 9, right? So that means when x is 0, y is 9, right? So here's 1, 1, 3, 5, 7, 9. So I'm at this point right here. This is 9, 0, so I'm going to go down here. Right there are these 2 points graphed. I'm going to take a straight edge and connect the points. And then they always tell you to label the line. All right. Now, instead of writing this out here, I like to just say this is line 1, this is line 2, So that's line 1. The book teaches you to write this out here, to write that this here is the x plus y equals 9 line. Now I'm going to graph this. This is 0, negative 5. So when x is 0, this is 5. So we have 1, 3, 5. So there's that point. And then this is 5, 0. So we're going to come over to 5. And y is 0. And we got those 2 points. We are now going to connect them. All right. So this is my line 2. Or if you want to label it correctly, x minus y equals 5. So these are your 2 lines. And now you have to determine what is the intersection of these points. And if you look, it's going to be, if I come over here, it's 7, and it's kind of halfway in between. And so this point where they intersect right here is 0.72. Now you have to do this on graph paper. You do have to use a straight edge in order to find the solution. So this is the solution because this is the only place that these 2 lines intersect. All right, so you're going to say the solution, right, is 7, 2. And you can do your check step. The check step is you plug in 7, 2 for this equation, 7, 2 for that equation, and see if you get true statements. All right. To save time, I'm not going to do that at this moment. All right, so now let's look at this particular example. Again, it says solve the system by graphing. So we're graphing, right? So again, I'm just going to find my 2 points. For each line, I'm going to graph both lines. That's all that's required here. Okay, so when x is 0, I end up with y equals 6 over 2, which is 3, right? So y equals 3. Just go ahead and write it that way. Okay, so that's when x was 0. When y is 0, what is x? Well, the x equals 6. So that means 6, 0. So here's my 2 points for this line. I'm going to graph them. So it's going to be 0, okay, and then 1, 2, 3. And it's going to be 6, 0. 1, 2, 3, 4, 5, 6. Now again, like I said, you need to use graph paper when you're doing these, but so to be accurate. And this here, this is line x plus 2y equals 6. That's that line right there. Now I'm going to graph this one by finding the x and y intercept. So if this is 0, then I get y equals 0 divided by negative 2, but 0 divided by negative 2 is 0, right? 0 cannot be negative or positive. So when x is 0, then y is 0. And now let's plug in 0 for this one. We get x minus 2, and let's see what the x is. Again, we get 0, 0. Let me just pause that for a minute. Okay, so I want to just continue. So as we do the x and y axis, you notice that we get the same point, the origin. So that means we can use the origin, but we've got to find another point. So we're just going to pick a point. I'm just going to say when x is 1, okay, or when y is 1. It doesn't matter. I'm going to make y 1. What is x? So I'm going to take this original equation, all right, and I'm just going to say, okay, well, when y is 1, what is x? Well, we get x minus 2, add 2 to both sides, and we get x is 4. So in this case, right, it's 4, 1. No, it's 0. Sorry. Minus 2. Add 2 to both sides. Oh, because that's 0. Sorry. That's still going to give me 0, 0, isn't it? Hang on. Let me go back to it. Sorry. So this is going to give me x minus 2 equals 0. Then I'm going to add 2 to both sides. When I do that, I end up with x equals 2 because, right, 0 plus 2 is 2. So we get 2, 1 as a second point. This is our second point that we needed to get here. Okay, we had to do that because the x and y intercept is 0. In other words, this, if I graph that, the origin, right, 0, 0, well, I still need a second point. So I did 2, 1, right? So 1, 2, 1. Now I have that. I'm going to go ahead and connect here using my straight edge. All right. And this line is the x minus 2y equals 0. So that's that line, and this is this line. And so then you got to find out where they intersect. Well, they intersect at 1, 2, 3. If I go up 3, this is 1 and this is 2. All right, so it's about, the point is 3 and 1 1/2, or 1.5. So that's your solution, or that's your intersecting point. All right, so your solution is 3 and 1.5, because that's the only point that would work for both equations. Now, I kind of know what it is here, so I'm just using a rough graph. But again, I'm going to say you have to use graph paper to get that exactly the exact point, okay? Now you can do the check step. Let's go ahead and do the check step for this one, just so you can see how to do the check step. So if I wanted to check, I'm going to take the original two equations, and I'm going to plug in my solution here for both of them and see if I get a true statement. So here x is 3, and y is 1.5. And here y is 1.5. This is going to give me 2 times 1.5 would be 3. Okay. And we get 6 equals 6. And this is going to give me 3 minus 3. And so we ended up with a true statement in both cases. So this right here is our solution, and we have done the check step to make sure we didn't make a mistake. All right.